end of the lesson, you should be able to name the components in a CPU, describe the machine cycle, and discuss processing techniques used by the operating system. Yes, Ma, I am eating 3 square meals a day. I know Brussels sprouts are my buddies, you know, I know. Listen, oh, I've just deleted it. No, Ma, I haven't deleted you. I have to phone you back. I'm busy at the moment, Ma. Okay, bye. Bye. Hey, hi there, and welcome to another lesson in our IT series on hardware and system software. Now, I wanted to do some research for you guys whilst talking on my phone at the same time. In other words, I was trying to multitask without much success. Nothing gets done. If only I had a built-in CPU right here. Maybe that's not such a good idea. Anyway, so far, we've learned a lot about the motherboard and connectivity. Now in this, the last lesson in our series, we're going to find out what components are on that tiny little CPU chip and how this dynamite in a small package goes about its business. But before we look at the CPU, let's just check that we know exactly what's in the signals carried by the buses. Each signal is a 0 or a 1 called a bit. By taking a group of bits, say 8 of them, that travel one after the other as in serial communication, or next to each other as in parallel communication, a computer system now has a pattern of bits that can be given a meaning. This is called a computer word. The messages carried by the buses can be data, instructions, addresses, or signals to indicate a task that has been completed. The computer's word length was 1 byte, or 8 bits. But as technology improved, more bits were needed to represent more things it could do. These days, 32-bit buses are common. The system bus is a 32-bit bus between the RAM and the CPU. But many newer computers have 64-bit technology. The CPU has 2 main sections: the CU, or control unit, and the ALU, the arithmetic and logic unit. Both of these have very small storage components called registers. A register can only store 32 bits at a time, exactly the number being brought in by the system bus. So, a CPU with 32-bit registers is called a 32-bit processor. It stores one piece of data, for example, the number 26, or one machine code instruction, or one address. Now, before you panic and say, what, just one instruction? Don't forget that the average typist can type about 120 words per minute. Now that's 2 words per second. The average CPU can process 3,000 million instructions with a word length of 32 bits in exactly the same amount of time. And every CPU has circuitry that tells it how to process. This is what's called its instruction set. And if it doesn't recognize an instruction, it can't do it. Now, fortunately, the people who created programming compilers knew exactly what they were doing. Every program written in a high-level programming language is translated into machine code before it gets sent to the CPU. These files are called executables, and they have a .exe as an extension. Now, let's see what's inside a CPU. The CU, or control unit of the CPU, has to manage the fetching, storing, and returning of processed data to RAM. It sends 2 signals on the system bus to the RAM. One is the address in the RAM, where the instruction or the piece of data is. The other is a read-write signal to tell the RAM whether the data must be sent to or is being received from the CPU. It sends these signals on 2 different parts of the system bus. The read-write signal is sent on the control bus, and the address is sent on the address bus. The data and the instructions fetched from the RAM are carried on the data bus. When they arrive in the CPU, they are placed in different registers. Processed data also returns to RAM on the data bus. The ALU processes one instruction at a time using a machine cycle, and the steps in the cycle are: fetch an instruction from the RAM, decode the instruction according to the instruction set, fetch or transfer data from RAM if needed, execute or carry out the instruction. These steps are repeated for each new instruction. Now, a fast CPU wouldn't be much use if it had to wait for instructions and data to arrive. Now, RAM is much slower than the CPU, so special high-speed memory called cache memory is provided. Now, a block of data and a block of instructions from the program in RAM are brought to the cache. The CPU has a special prefetch unit which fetches only data and instructions likely to be needed next. Special algorithms are used to predict what will probably be used. Level 1 cache is found in the circuitry of the ALU and runs at the same speed as the processor. Level 2 is slower and is found on the CPU chip. Level 3 is the slowest, but still faster than RAM, and is found on the motherboard of older computers. So, that's how the CPU works. If you press Ctrl, Alt, and Delete on a Windows computer, you'll get the Task Manager, and you can see which applications are running. If you click the Processes tab, you can also see which processes are being run. What's the difference between an application and a process? The user may have started an application, but only the processes the CPU is using at this moment are shown here. For example, I'm not printing now, so we won't see the printing process for my application here. There are also processes which the operating system has started running in order to manage the computer. If you want to see how hard your CPU is working, click the Performance tab, and you will generally find it running at a very low percentage of its capacity. That's normal. It's so fast that it has a lot of idle time, waiting for more instructions. Now, the operating system, which manages all the hardware and software, must tell the CPU when to start and how to do complicated jobs like multitasking. Now, Morwa and Zamo had a school project to do on the role of the operating system, and they're coming in to do a final check before they hand in their project. So, I'm going to leave you in their very capable hands. I'll see you later.
Oh, Zamo, for a change, this project was really interesting, hey?
I know.
I reckon we should do well.
I know, I'm hoping for an A. Oh boy, our teacher's going to be so surprised. For once, I actually did some work.
And who had to nag you? Right, now let's quickly go through the questions, okay?
Okay.
Number 1. What's the difference between a program and a process? Explain and give an example.
Hey, what a coincidence.
What?
Oh, nothing, I just wonder how this happened.
Look, Zamo, we're not going to get much done if you keep getting distracted.
My computer is showing the task manager. Now, the program that's actually running is in applications, but the processes of the CPU are listed under processes. I'm going to press print screen so we can copy this and add it to our project.
Whatever. Anyway, back to the project.
Yeah.
Okay, we wrote, a program is stored on the hard drive. It might consist of a number of executable files to do different things for one program. For example, one file plays the sound for a game, another moves your character around the screen, and a third handles a task which is seldom done, like changing the way your character looks. When you click to run the program, most of the program's files are loaded into the RAM, but because you seldom change your character, that file is only loaded when you need it. If you turn off the sound, that file is in RAM, but is not sent to the processor to be executed. Therefore, a program is all the executable files or instructions, and a process is an executable file currently being processed.
Okay, next question. Why is an operating system needed, and how does it manage the processes? In your answer, you refer to the management of memory and how it relates to processes. And I like the cartoons you drew explaining why we need an operating system.
Oh, why, thank you, kind sir. I also pointed out that someone or something must decide on which process to run, when to start it, and when to stop it, and how many processes can be run at the same time. Hey, we didn't think about the user. Doesn't he start the process?
No ways! When a user clicks on an icon to run a program, he's just getting the frequently used executable files into the RAM. He doesn't control anything after that, unless he wants to find out how to allocate RAM to the program, or how to tell the dual-core processors which processors to run, and which of the two processors should run it on. Now, let's have a look at your cartoons again.
Once you get it going, the CPU will process whatever you throw at it. Imagine if the CPU decided what to run.
Old prefetch unit here is too busy figuring out which instructions and data in the process are likely to be needed next, so he can get it into the cache to feed the speedy ALU. And control unit just wants to get everything to the right address and moving in the right direction.
Yeah, it's definitely not the CPU who calls the shots, and it can't be RAM either. He just stores stuff. The RAM reminds me of those people at the check-in counter in supermarkets who keep your parcels. They put your goods in a pigeonhole and give you a disc with a number on. They don't care what you've got in your parcels, and they don't tell you what to do while you're away. RAM doesn't care a hoot what the CPU is up to, and everything it stores is just zeros and ones. Oh, what a boring job. Zamo, we should add a label that says, "Don't handle with care. The contents are already in bits."
So, we concluded that the hardware cannot communicate with the software without some help. And to make decisions, control, and manage the system, we need special software.
I didn't do a cartoon for it, but we said that the job couldn't be done by the user because it's too complicated and a computer must be controlled electronically.
Right, and that's where the help from the operating system comes in, which was designed by people who do know all the messy details. You know, it just struck me. BIOS stands for Basic Input and Output System, which is kind of like a mini operating system, except without a user-friendly interface. Let's reboot and I'll show you.
It's interesting to see what settings are stored in the CMOS, but you can't change some of them. Why is that?
In most cases, you use software to change the regional settings, i.e. things you're allowed to change. Once the BIOS has checked that all the hardware works, it reads the ROM chip on each device. This tells it things like how much RAM the device wants. It also gives the device a number channel so that it can signal the CPU that it wants attention. And that information gets stored in CMOS. And that's what Morwa and Zamo are looking at right now, the contents of the CMOS. And from there, the BIOS runs its bootstrap loader program. This tells the CPU to process whatever program loader file the operating system put in the boot sector when it was installed. This file holds the instructions for loading the operating system into RAM. Then, once it has control, the operating system can allocate RAM addresses for the printer using the figure stored in the CMOS settings. And it's better not to fiddle with these settings even if you can. Your operating system won't be very happy if you go confusing it with funny things. The BIOS has to allocate different parts of the RAM to different programs, as well as create buffers for the printer and the keyboard.
The CPU doesn't jump every time you press a key. Instead, it waits for a couple of keys to be pressed, stored onto the buffer, and then puts them onto your document as one data transfer. That way, it doesn't have to waste resources on transferring only one passenger in the bus, and it doesn't have to run that process so many times.
What process?
The one that takes the letters from your keyboard onto the document. Anyway, we're getting distracted here. Let's see what we wrote on how the OS manages the processes.
Okay, luckily the teacher said we can be brief here. We said the OS uses a program called the scheduler to determine which process to run and when to run them.
Also, if the printer has to print large amounts of data from many files, the OS uses spooler program to queue them up into the file called a spool file on the hard drive. Then, the RAM is free to do other work while the printer reads its data from the hard drive instead of the RAM.
When a user or the OS wants the CPU to do several things at the same time, the OS instructs the CPU to do a few instructions from each process in turn. The processor is so fast that it appears that many programs are running simultaneously.
Isn't multitasking what you girls claim to do? Anyway, I can do multi-threading. Listen. Programmers can write one program, but use different parts of the program to do different things. These parts are called threads and are designed to be run at the same time. Now, the CPU must be built to handle threads. And if the OS detects that the program is multi-threaded and the CPU can run threads, it instructs the CPU to use multi-threading. You see, boys can do more than one thing at a time. Girls just appear to be doing it. And the ones that I've seen trying to do multi-threading just gets their threads tangled up.
Yeah, well, multiprocessing was easy. Anyway, some CPUs have two processors on the same chip, as well as two sets of registers. They are dual-core CPUs, and each of the processors does the same work that one would do. But the OS shares out the processors equally between them. This means that several processors can run at the same time on different CPUs.
And the chipset on the motherboard, as well as the operating system, must be capable of running multi-core processors. Hey, what's this here? We didn't do hyper-threading.
Zamo, I got so sick of nagging you to do some work that I finished off the project by myself. Hyperthreading was a technique developed by Intel for their Pentium 4s before there were dual-core processors. A hyperthreading CPU also has two sets of registers but only one processor. One thread goes to each set and is ready for the processor to switch quickly from one to the other. That makes hyperthreading faster than multi-threading but slower than multiprocessing.
Thanks for doing that.
No problem. But at least I'm finished and it will give us time to play games on your computer tomorrow. And we must think of a brand name, seeing as we made it. How about Hermade?
You've got to be joking. I want a really cool name.
Okay, how about Bits and Pieces, seeing as that's how we made it? Or Bit Buddy, or Zamu's Bits. Wait, get this. How about One Bit Short of a Butt?
No, I'll get you for that.
Okay, but just don't mess up the project, Mr. A+.
So, you should be able to understand and explain what a CPU does. Now it's time for today's task. Select one of the techniques used by the operating system to control and manage the CPU and RAM. Draw and label an A4-sized diagram that shows the CPU with the correct components for that technique. Now, people should be able to understand the technique just by studying your diagram. And as a final tip for the task, don't forget, the operating system controls all the hardware and the software. Well, that's it for this series. So until next time, adios amigos. On that tiny little CPU chip and how this dynamite in a small package goes about its business. But before we look at the CPU, let's just check that we know exactly what's in the signals carried by the buses. Each signal is a 0 or a 1 called a bit. By taking a group of bits, say 8 of them, that travel one after the other as in serial communication, or next to each other as in parallel communication, a computer system now has a pattern of bits that can be given a meaning. This is called a computer word. The messages carried by the buses can be data, instructions, addresses, or signals to indicate a task that has been completed. The computer's word length was 1 byte, or 8 bits. But as technology improved, more bits were needed to represent more things it could do. These days, 32-bit buses are common. The system bus is a 32-bit bus between the RAM and the CPU. but many newer computers have 64-bit technology. The CPU has two main sections, the CU, or control unit, and the ALU, the arithmetic and logic unit. Both of these have very small storage components called registers. A register can only store 32 bits at a time, exactly the number being brought in by the system bus. So, a CPU with 32-bit registers is called a 32-bit processor. It stores one piece of data, for example, the number 26, or one machine code instruction, or one address. Now, before you panic and say, what? Just one instruction? Don't forget that the average typist can type about 120 words per minute. Now, that's 2 words per second. The average CPU can process 3,000 million instructions with a word length of 32 bits in exactly the same amount of time. And every CPU has circuitry that tells it how to process. This is what's called its instruction set. And if it doesn't recognize... I have to phone you back. I'm busy at the moment, Mark. Okay, bye. Bye. Hey, hi there, and welcome to another lesson in our IT series on hardware and system software. Now, I wanted to do some research for you guys whilst talking on my phone at the same time. In other words, I was trying to multitask without much success. Nothing gets done. If only I had a built-in CPU right here. Maybe that's not such a good idea. Anyway, so far we've learned a lot about the motherboard and connectivity. Now in this, the last lesson in our series, we're going to find out what components By the end of the lesson, you should be able to name the components in a CPU, describe the machine cycle, and discuss processing techniques used by the operating system. Yes, Ma, I am eating 3 square meals a day. I know Brussels sprouts are my buddies, you know, I know. Listen, I've just deleted it. No, Ma, I haven't deleted you.